In this video, we're going to talk about a super important topic, which is security in Kubernetes. And what are some of the best practices for securing your Kubernetes cluster? The big challenge that we see in terms of Kubernetes security is that it's already so challenging to set up a Kubernetes cluster and to configure it to deploy the applications in it that security often becomes the afterthought, adding on top of that already complex configuration. However, we can't deny the importance of security, especially when the systems are so complex. So first of all, let's talk about security in cloud in general. We have a trend that more and more workloads are moving to the cloud. And often there is a misconception that cloud is secure by default. So people think that because the application is on cloud, it is protected. But it's important to understand that you have to secure and manage the infrastructure and your applications on the cloud just the way you manage them on premise. The difference is that on cloud, you simply have different tools and technologies to configure that security. And often, many organizations aren't aware of those tools or aren't using the tools that are available for making your cloud environment secure. So with all these things combined, cloud applications actually become a very attractive target to a lot of hackers. And this growing number of cloud-native applications mostly use Kubernetes as a platform. And that's where the relevance of knowing how to secure Kubernetes clusters comes into play. So the question is, how secure is Kubernetes by default? So if I don't do anything explicitly and take the defaults, what is my security status? So what are we starting from? And what are the vulnerabilities or security gaps that we have in Kubernetes? And what are the security best practices to protect and close those gaps in Kubernetes to secure our systems? The common number one issue is when someone gets access from Kubernetes platform to the underlying operating system, in which case an attacker can do a lot of damage to the whole system. And this can happen because of various misconfigurations. And we're going to talk about those and how to protect your Kubernetes so that this doesn't happen in this video. When we talk about security, it's also important to understand that security is a combination of multiple things on multiple levels. So it's not just one or two things that you do that basically just secure everything. In case of Kubernetes, we have the underlying infrastructure, then the Kubernetes platform that is running on that infrastructure, and the applications running inside Kubernetes platform. So all these levels need to be secured individually, which is quite a challenging job. And one of the main challenges of security in general is that the attackers have an advantage because they just need to find one security weak link in the system to attack, while a defender has to defend every single point, maybe multiple times, to prevent that from happening. In many cases, we would need to defend each point with multiple different mechanisms. So while coding best practice is not to repeat logic, security best practice generally is actually to be redundant. So use many security mechanisms in place to protect every attack point. So this way an attacker will have to do multiple things in order to get into your system or access your valuable resources and basically do some damage to your whole environment. Now, before we dive in the 10 security best practices, I want to say a huge thanks to Kasten for sponsoring and making this video possible. They have an amazing tool called K8s, which is the Kubernetes backup and restore solution. It is a Kubernetes native application and has a lot of really good features for backup and restore use cases. And apart from backup and restore being an important part of security mechanism itself, and we're going to talk about that in this video, K8s actually has a big focus on all the security aspects in Kubernetes. So it integrates with various tools and is basically engineered to make it easy for Kubernetes administrators to secure the K8s service itself in the cluster. So with that, let's dive in our 10 security best practices for Kubernetes. First of all, what is the main purpose of Kubernetes? It is to run applications inside, right? So we have built an application and we need to deploy it in Kubernetes as a container. And securing workloads in Kubernetes starts before they even get deployed there, when we build a container image which will eventually run in the cluster. So building a secure image in the CI/CD pipeline is the first step. So what security issues do we have here? Images are built in layers, and each layer contains a command or a tool configuration, etc. So there are things that basically go into building the image. We install different tools, maybe we create some users, and so on. So we need to be thinking about everything that goes inside that image, and what is the security impact of that. First of all, code from untrusted registries. We may be using a code or a library in our application which comes from an untrusted source. So we have an untrusted code that may include some virus or backdoors that could unintentionally grant access to an attacker. We may also be using some packages for an operating system in our Docker image. So these dependencies and tools may also have some vulnerabilities, or the base image that we're using to build our own application image may have some vulnerabilities. So this means we need to be careful what goes inside the image, what libraries and dependencies and tools we're using when putting together our application image. Generally, when we're building images, developers should eliminate any unnecessary packages, libraries, and dependencies that application doesn't necessarily need, or it may need in a build time, but not necessarily in runtime. And also they should choose leaner and smaller base images with less tools inside to build the application image, because mostly you don't need so many tools to run your applications. If we do build an application image with some vulnerabilities and it gets deployed to the cluster, that may introduce serious security issues. For example, an attacker may use a vulnerability in an image to break out of a container and get access to the host or the Kubernetes worker node. And from the host, they can access all the other containers running on that host. So they will be able to do much more damage if they manage to break out of the container. They can read data in the host volumes, they can read the file system, and so on. They could also read the configuration of kubelet that is running on that host, including kubelet's authentication token and the certificates that it uses to talk to the Kubernetes API server. And that will give an attacker a chance to do further damage to the cluster and escalate privileges. So a lot of serious security issues may arise if you have vulnerabilities in your image that will allow an attacker to access the underlying host from a container, for example. So how do we prevent any such vulnerabilities and issues from slipping in to the image when we're building that? Well, we should do what's called image scanning. So the first security best practice is to do image scanning and make sure to build secure images. And there are a lot of tools out there that can help you in that. For example, you have Sysdig and Snyk, etc. that basically have a database of vulnerabilities that get updated regularly, and they will basically do the scanning of your image against those known vulnerabilities. So you need to make sure you're constantly scanning for vulnerabilities. So how do you do image scanning exactly? Using the image scanning tools that I mentioned, you can scan the images in the CI/CD pipeline, for example, before pushing the image to the repository. So once the image is built, you can run a command of that image scanning tool that checks the image for any insecure tools or packages or dependencies with any vulnerabilities, as well as it also checks for an insecure configuration and any hard-coded secrets, for example. So once the image is built and it basically passes that vulnerability scan or security scan, it can be pushed to a repository. However, it could happen that a vulnerability gets discovered after an image was scanned and pushed to the repository. As I said, tools like Snyk, for example, they have a database of vulnerabilities that gets updated constantly when new ones get discovered. So a lot of image registries like Docker Hub and so on actually have a feature for scanning images in the repository itself, which means it's also important to scan images regularly that have already been pushed to a registry to make sure there are no vulnerabilities that appeared after the image was built. Another security best practice is to avoid using root user in your containers and running your containers with privileges. If you have a vulnerability in an image and it's running with a root user, the attacker can much more easily use that to break out from the container and access the host or the Kubernetes worker node. So when building your image, you should create a service user and run the application with that user instead of using the root user. But note that even if you build the image like that, you could actually override that in the pod configuration itself. So you might have an image that runs with a service user, but you can actually configure or misconfigure a pod to allow it to run with root or run it as a privileged container, or even allow access to the host network, which is not a good thing. And if this kind of misconfiguration slips into the cluster, your pod now becomes very insecure. So avoid running privileged containers to make it harder to break out from it. Because this way, the attacker will have to first get access to the root user inside the container, and then they will be able to break out and access the host. Now, once our application is deployed and running in Kubernetes, we have a number of things to secure inside the cluster itself. First of all, who can access the cluster? Which human or application users? Once inside the cluster, what can these actors do? What are their privileges? This becomes more relevant if an attacker steals an identity of one of these authorized parties. Because then the question is, what can an attacker do in the cluster? What permissions do they have? Therefore, we need to manage users, roles, and their permissions in Kubernetes. And we need to keep these permissions as restricted as possible. If someone in the team needs access to troubleshoot or debug pods in my app namespace, then they should be given read-only permission to Kubernetes resources in that namespace only. So how do we manage users and their permissions in Kubernetes? For that, we have RBAC, or role-based access control. And these are Kubernetes resources that allows you to create roles in Kubernetes with certain permissions. For example, a role that allows viewing, creating, and updating deployments, services, config maps in a namespace called database. So that would be one role, right? So what can you do with which resources in which namespace? Or you may have a role that allows only viewing and listing pods in a my app namespace. Now the roles need to be attached to actual users, like a team member, Sarah, who is deploying and managing database services in a cluster, can get the first role associated to her user. And a junior developer, Tom, can be granted the view-only role to be able to see what pods are running in a my app namespace. In Kubernetes, there is actually no resource for user. So you can't directly create user components in Kubernetes. Instead, the users are indirectly created by either importing a list of users into your cluster, or, for example, by generating a client certificate for the Kubernetes API server for a specific user. So in our example, client certificates will be generated for both Sarah and Tom for the Kubernetes cluster, and the user for that certificate will be registered as a user in Kubernetes. And once you have that, user Sarah, user Tom, both with their own client certificates associated to the cluster, you can then attach those roles with the respective users. Now, you also have a Kubernetes administrator that needs to be able to create and update resources in multiple namespaces, or maybe the whole cluster. And for that, we actually have cluster roles, which are the same as roles, but they apply to the whole cluster instead of a specific namespace. So, for example, Kubernetes administrators, Kate and Mark, can both get cluster roles associated to their users that allow them to create, view, and delete a list of different resources in all the namespaces in the cluster. As I mentioned, you also have non-human users. For example, if you're deploying to Kubernetes cluster from a Jenkins pipeline, or running a third-party service like Istio, for example, that needs access to Kubernetes resources and needs to talk to Kubernetes API server, you need to give those tools access to the cluster as well. And for non-human users, there is actually a Kubernetes resource dedicated for that called service account. So the way it works is that every pod in Kubernetes gets a service account which they can use to talk to Kubernetes. And service account, just like human users, has roles associated to it with some permissions. And while users have client certificate to authenticate with the API server, the service account uses token to authenticate. So it's important to know exactly and limit the permissions a service account has, because if an attacker got access to a pod, they can use the service account token of that pod to send requests to the API server and create, change, and delete resources if they have permission to do it. So as a security best practice, you need to use RBAC to manage access permissions in your cluster and know exactly who has access to what, and also use the least privilege approach. Now, using RBAC will manage the permissions of external users and what they can do inside your Kubernetes cluster. But what about inside the cluster itself? The communication between the services. By default, in Kubernetes, each pod can talk to any other pod inside the cluster. This means if an attacker gets access to one pod, they can access any other application pod. Now, in reality, not every pod needs to talk to all others. So we can actually limit the communication between them and create network rules in the Kubernetes network layer that determines exactly which pods can talk to which other pods, and also which pods they can receive traffic from. And you can do that with a Kubernetes resource called network policies. So using network policies, you can define a rule that, for example, a front-end service can only talk to the backend service, but it cannot talk to database or an authentication service that are running in the cluster. And you can define that database pod can only receive traffic from backend pod, and so on. So for maximum security, you can apply the least access allowed rules here. So you define each and every communication rule between all the pods. So now if an attacker gets access to one of the pods, they won't be able to talk to all others that may be running sensitive applications and holding some sensitive data. And also note that network policy resource itself is actually implemented by a Kubernetes network plugin like Calico or Weave, etc., that you deploy in the cluster. Now, network policies configure communication rules on a network level. But if we want to define these rules on a service level or an application level, which is a more logical level, so to say, we can use a service mesh like Istio for that. So Istio uses proxies in each application pod that will control the traffic coming into the application as well as traffic going out of the application. So you can configure communication rules between the services on a logical level that will then be controlled or checked by the proxies that Istio uses. So using network policies or service mesh to define stricter communication rules between the pods is another security best practice. Another part of pod communication is that by default, the communication between pods in Kubernetes is unencrypted. So if an attacker manages to get inside the cluster, they will be able to see all the internal communication between the pods in plain text because none of it is encrypted. With service mesh like Istio, in addition to defining the service communication rules, you can also enable mutual TLS between the services. So all the communication between them will be encrypted. And that means if an attacker sees the traffic inside the cluster, they won't be able to read it. So encrypting cluster internal communication is another good security practice that will give you an additional layer of security. Another thing which is not secure in Kubernetes by default is the secrets. You probably already know that for sensitive data like credentials, secret tokens, private keys, etc., we have a secret resource in Kubernetes. However, by default, secrets are stored unencrypted. They are base64 encoded, so anyone who has permission to view the secrets can simply decode the contents of a secret and see them in plain text. So again, if an attacker gets into a cluster with an access to the secrets, they will be able to read all the sensitive content. So how can we secure secrets in Kubernetes? Well, there are several ways. The Kubernetes own solution is to enable and configure encryption using the encryption configuration resource. However, this still has an issue because you still have to manage the encryption key itself and store it somewhere securely. So some third-party tools can be used for this, like AWS KMS, which is Key Management Service, for example, can be used to manage the encryption keys. Or a service like Vault from HashiCorp can be used to securely store the secrets themselves. And Vault would actually take over storing and managing the secret data. So securing and encrypting secrets is important and another security best practice. Now, secrets and all other Kubernetes configuration data are actually stored in a key value store in Kubernetes called etcd. So Kubernetes uses this etcd store to keep track of and update its configuration and all the resources like services, deployments, pods, etc. And every single update gets saved into the etcd store, and the same way any change directly to the etcd will lead to changes in the cluster. This means if an attacker can get access to the etcd, they can bypass the API server and make changes directly to the etcd store, which will then result in Kubernetes resources being updated. And this would be actually an equivalent of having an unlimited access to the whole cluster where they can do anything they want, destroy, update resources, get access to the data, and so on. So another good security practice is to secure your etcd store. There are a lot of ways to do that. There are a lot of alternatives of how an etcd can be run for your Kubernetes cluster, whether inside the cluster itself or outside, managed separately. But generally speaking, it's a good practice to put your etcd behind a firewall and allow only the API server to access it with proper authentication. In addition to that, the whole etcd data can be encrypted, so even if the attacker gets access to it, they won't be able to read it. Now, etcd stores the cluster configuration data. So these are all the Kubernetes manifests that define the Kubernetes resources like deployments, services, pods, etc. But we also have the application data, like data stored by database services. And the biggest security damages for any company are related to data, especially the personal data. Stealing data like credit card information of your users or medical records or leaking of any private data is the worst scenario for any company when an attack happens. But in addition to that, you also have risks of attackers wiping out your data or corrupting it, so you basically lose all your application data. This means you can't recover your application after the attack because all the data is gone. So one thing that attackers commonly do is taking your data and requesting a ransom for it. So you have to pay them to get your data back. And you have to be protected for all these scenarios. And that's the next security best practice, to have a proper automated backup and restore system in place for your cluster that regularly backs up your data and stores them safely so that you can use it to restore your cluster when a disaster happens. And Kasten's K10 is actually a Kubernetes native tool that you can use to configure this automated backup and restore. And since, as I mentioned, K10 is so focused on security, they have all the mechanisms in place to both transfer the data as well as store that backup data securely and encrypting it throughout. Now, in addition to attackers corrupting or stealing your data, the attacks may be so advanced that they will try to get the backups as well. So they will corrupt the database data plus all the backups that you have for the data. This means, again, you are not able to recover your application and maybe have to pay a ransom to get back the data. So you need to protect those backups as well. And what K10 offers as a solution is that you have immutable backups, which means they can't be manipulated or corrupted. And a big advantage of K10 is also that you can back up all the Kubernetes related data with it. So not only the application data in Kubernetes, but also the data outside Kubernetes, plus the etcd stored data. And this is great because you have one tool and one automated mechanism for all your relevant backups for your cluster. If you want to know exactly how K8s backup and restore mechanism works, I actually have a separate video on that. So you can check out the link here or in the video description. Now let's say as a Kubernetes administrator, you know and apply all these security practices and try to protect your data and your cluster by configuring everything properly. But Kubernetes cluster is usually used by developer teams who deploy their applications and services in it. So you may be doing everything right, but how can you make sure that all these developers also apply these security practices when deploying their applications? Maybe their pod configurations are super insecure because they don't have enough knowledge about security configuration best practices. And you can't just manually check everything they deploy to the cluster. So how can you deal with such a scenario? Well, for that, there are what's called security policies in Kubernetes. With security policies, you can define some rules, such as pods that run privileged containers or container with root user cannot be deployed, or that a network policy needs to be defined for every pod, and so on. Security policy resources in Kubernetes are implemented by third-party tools, like Open Policy Agent or Kuverno. And usually the way it works with these tools is that you create this security policy definition in Kubernetes with all the rules, and security policies hook into the Kubernetes admissions controller component, which decides whether the deployment can go through based on the policies that you defined. So it's like a gatekeeper that validates deployments against the policies defined by you. And this way you can have automated validations for various security configurations. So creating security policies to automate validation for security configuration is another security best practice. Now, let's say we apply all these security practices, but you cannot always 100% protect everything, right? As I said at the beginning, an attacker just needs to find one weak spot to succeed in the attack and do some damage. So you may still get an attack that messes up your cluster. And here it's important to have a proper strategy and mechanism for disaster recovery. So what do you want to do in an attack scenario? Well, you want to restore your cluster with the backup data and get it up and running within a short time and make your application available to your users again with minimal effect on user experience. So the last security best practice is to have a mechanism when an attack actually happens. And for that, you need a tool that allows you to recover the cluster in the same state with the latest backup. So again, tool like K8s has a feature to take the last backup and let you do the disaster recovery in an automated way. And an important emphasis here is on the automated recovery, because in such a scenario, when your system is under attack, you don't want to be manually recovering your cluster under a time pressure. Instead, you want to have a tool that automatically does that for you. And ideally, you'd actually test your K8s recovery so you know exactly how it will work and what results it will give you when you run it in case of a disaster. So executing an automated, well-tested recovery plan can minimize the effect of the attack and get your application up and running very fast. And note that K8s also allows you to recover your cluster to any environment. So it doesn't have to be exactly the same environment with the exact same Kubernetes version as you had. Instead, you actually have a freedom to choose to recover your system in a completely different environment using maybe a different storage class, etc. So you're not tied to a specific type of underlying storage infrastructure or even a specific Kubernetes distribution. Now, I could talk for hours about security practices in Kubernetes and go into detail because there are a lot of topics around it, which we will actually be covering in our upcoming DevSecOps course. If you're interested generally in security in DevOps, then you can sign up for the waiting list and be notified when we release the course. Well, I hope the security practices that I explained in this video were already super helpful. Please comment and share your experiences with security in Kubernetes and which security practice that I haven't mentioned here is also very important. And with that, thank you for watching and see you in the next video.